Welcome to today's explainer. We're jumping right in because we're looking at something that literally hides in plain sight in almost every industrial environment. We're pulling back the curtain on the surprising complexity behind a component that usually gets totally overlooked: the wiring duct. Yeah, those plastic or metal channels running through electrical cabinets. You might think they're just there to, hide wires, but the reality is way more fascinating and highly regulated.
Think about it. When you open a control panel, what's the actual backbone that keeps it safe and serviceable? It's super easy to assume it's the high-end PLCs or those heavy-duty contactors. But look, without a structured way to route, separate, and protect those connections, you don't have a system, you have a rat's nest. And a messy panel isn't just an eyesore, it's a massive liability.
Okay, let's dive into this. The answer? It's the wiring duct. It dictates how we route conductors, separate voltage classes, and actually plan for future expansion. And here's the kicker. You can't just slap it in however you want. It's strictly governed by standards. And the true star of today's explainer is why the UL 508A standard governs this so heavily.
Here's our roadmap for today. First, we'll look at the unsung hero of the panel. Then, the law, UL 508A and other standards. After that, we'll open up the toolkit to examine duct types, dive into the actual math of duct sizing, and finally wrap up with perfecting the panel layout itself. Let's get to it.
Section 1. The unsung panel hero. More than just tidiness. So, before we get into the heavy standards and the math, we need to establish exactly why we even care about cable management. The walls of these ducts are actually doing a ton of heavy lifting. First off, they physically shield conductors from sharp edges and rotating parts inside the panel. This protects the insulation from abrasion over time. Second, by creating defined paths, they limit electromagnetic interference, or EMI, between high-power circuits and sensitive signals. Third, they make troubleshooting infinitely faster, because every single wire follows a predictable route. Plus, let's be honest, a neatly ducted panel screams quality to any inspector who opens that door.
Section 2. The law. UL 508A and standards. Because cable management is so absolutely crucial to safety and uptime, regulators basically refuse to leave wire duct selection to chance. Enter UL 508A. So, the crucial point here is that this is the United States benchmark for industrial control panels. It actively defines the exact wiring methods, how conductors must be separated, and the strict expectations for duct fill. Duct design isn't just an aesthetic choice, right? It's a meticulously calculated compliance measure. If you want that panel certified, you got to play by these rules.
Now, UL 508A doesn't operate in a vacuum. It sits alongside other critical codes to ensure disciplined routing everywhere. You've got NFPA 79 governing electrical safety on industrial machinery. There's NEC Article 409 covering field-installed panels under 1,000 volts. And if you're building for the international market, IEC 602041 plays the exact same role for global safety. Together, these standards really push designers toward total discipline.
Section 3. The toolkit. Choosing your duct type. To meet these incredibly strict standards we just talked about, panel builders can't just grab any piece of plastic off the shelf. They rely on a mix of specific, purpose-built duct styles. On one side, we have slotted wiring duct. This features open slots with breakaway fingers. It's totally perfect for I/O zones and terminal strips where you have dense control wiring and, frequent rework. On the flip side, we have solid wall duct, fully enclosed. This is your go-to when you need to contain noisy servo drives or run EMI-sensitive analog cables. Most professional panels blend both styles to perfectly balance density and interference control. But the toolkit goes even deeper. We've got specialty options. Flexible duct is an absolute lifesaver for routing wires across hinged doors without snapping them after a few thousand cycles. Wide slot duct handles those really thick power conductors. Low-profile duct rescues you when you're dealing with tight backplates. And let's talk materials for a second. While PVC is the economical, durable default, metal raceways give you powerful EMC shielding. And if you're building for a food, pharma, or rail environment, halogen-free duct is straight-up mandatory to limit toxic smoke if there's ever a fire.
Section 4. The math of duct sizing.
Now, what's really interesting about this is how we translate those abstract code requirements into real-world mathematical outcomes. The golden rule of duct sizing is the 50% fill ratio. Industry best practice targets filling only 50% of the duct's internal cross-sectional area with conductors. Why? Well, because overfilling traps heat and makes future rework a total nightmare. You literally need that 50% empty space for heat dissipation and to leave generous headroom for additions down the road.
Here's exactly how builders budget their space to satisfy those UL 508 expectations. You take your duct size, calculate the total internal cross-section area in square millimeters, and literally just cut it in half. For instance, a 60 by 60 millimeter duct gives you 3,600 square millimeters of area. That means your target budget for wires is strictly 1,800 square millimeters. You just sum the cross-sectional area of every single conductor sharing that channel to make sure it stays under that limit.
Let me give you a snappy, real-world example to show how this actually plays out. Imagine taking 20 1.5 square millimeter control wires. If you place that entire bundle into a standard 40 by 40 millimeter duct, it actually consumes only 17% of the available space. I mean, that leaves massive headroom. That's the kind of deliberate mathematical planning that separates an amateur panel from a professionally engineered, standards-compliant assembly.
Section 5. Perfecting panel layout. Let's move on and see how this builds into the physical execution on the panel backplate to create a perfectly compliant layout. It all rests on a simple grid. Step 1, you lay vertical backbone ducts along the left and right rails. Step 2, cross your horizontal ducts directly above or below your DIN rail rows. By doing this, every wire follows a predictable path. A technician can trace a circuit visually without ever having to unclip and remove the duct covers. Then, you separate power and control and finish off with flexible duct and strain relief on any moving doors.
A massive focus of UL 508 when you're routing this grid is separation. Consider the difference between 24-volt DC signal conductors and 230-volt AC motor circuits. You absolutely cannot run these in the same duct. Mixing high-energy power paths with sensitive electronics is basically inviting capacitive and magnetic coupling. That injects noise that will completely corrupt your PLC inputs and analog readings. The standards require physical separation, either through dedicated ducts or solid internal dividers, to ensure safety and signal integrity.
This idea perfectly summarizes the core ethos of our explainer today. Wiring duct is not a routing afterthought. When you use the math, when you select the right materials, like slotted versus solid, and when you strictly apply standards like UL 508A, you aren't just following rules for the sake of it. You ensure the panel is easier to build, passes inspection flawlessly, and operates reliably for decades to come.
So I'm going to leave you with this final thought to reflect on your own engineering practices. When you plan out your next panel, are you genuinely engineering a structured backbone that leaves that 50% room for the future? Or are you just slapping down plastic covers to hide the chaos underneath? Remember, mastering the duct is mastering the panel. Thanks for learning with me today, and I'll catch you on the next explainer.